Now that we've laid the groundwork with an introduction to probability and we have a few axioms of probability, now we're going to establish a few useful theorems, right? So let's get right to it. So this theorem is called our general addition rule, right? And it basically describes how we find the probability of the union of two events, right? Any two events, right? So the statement is pretty simple. Let A and B be subsets of some sample space, then the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. So let's take a look at a proof of this. And the proof is useful because, not just that it establishes the result, but the way we establish the result. It kind of gives you an insight as to how you can approach some problems. All right. Students often think that a proof is just all completely theoretical, but the idea behind the proof actually gives you a roadmap that enables you to solve a lot of problems related to that particular topic. So, since this statement is about two events, let's draw the Venn diagram for two. So we have our two circles, right, partially overlapping like this, right? Now, the statement is talking about the union of A and B. Well, it turns out, yes, we can just think of the union as everything inside both circles, but really it consists of three like smaller regions that just don't happen to overlap. So here they are in three colors. So for instance, the A region can be written, I'm sorry, yeah, or the blue region can be written as A minus B, right, using our set minus notation. And the green region, well, that we know, we can express that as A intersect B. And then finally, the red region is just this one flipped around. It's just B minus A. But the important thing about all of these is that these are disjoint. They don't overlap, right? But if you were to take this set, and this set, and take the union of all three of them, you will get back the union of A and B, right? You'd still end up with everything inside those two circles. So it's kind of a clever way of writing the union. Now you might say, well, that just looks more complicated. Well, in a sense, but what you're doing is you're looking at the union with more detail. You're saying, like, what actually makes up the union? Well, it's all the elements that are just in A, all the elements that are in both, and then all the elements that are just in B, or B only, and you take the union of all of those, right? Again, that's another way we can write the union. So, if we take the probability of this, because they're disjoint, one of our axioms of probability says if you're taking the probability of the union of events that are disjoint, you simply add the individual probabilities together. So this would be the probability of A minus B plus the probability of A intersect B plus the probability of B minus A. Okay, now let's think about A minus B specifically. Well, A minus B would be taking all the elements in A and subtracting the portion that overlaps. So take all of A, but then take away the green part. So I can write the first term in the sum as the probability of A minus the probability of the intersection, like that. So this first expression can be written as this difference. And then I'm going to continue and write the middle term. So just bring down the probability of A intersect B. And then do the same thing for B minus A. If I take all of B and remove the region in green, right, that they have in common, that's just going to leave this part. So the probability of B minus A is the same as the probability of B, that's all of B, but again, take out the part that is shaded in green, which is, again, the intersection. And what happens is now you should be able to see the result. These two terms will cancel out, and what I am left with is exactly what the theorem says. So therefore, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection, right? And that's our QED. So we normally put our QED at the end of a proof. It's Latin for quo eratus demonstratum, which means that which was to be proven or demonstrated. So you make a claim, and then you justify the claim, and you say, yep, that's what I claimed. All right. So that's the first theorem, really useful. One more that we're going to look at, and this theorem is the complement rule. So you would expect it to involve the complement operation, and it does, right? So this is the complement rule. And this one is even simpler in its statement, and it's simpler in its proof. So this is what the theorem says for the complement rule. It says, let A be a subset of our sample space, then the probability of the complement of A is equal to 1 minus the probability of A, right? So let's say this one out in words. So this is saying the probability that an event does not occur is equal to 1 minus the probability that it does occur, right? And it's like, even when you say that in words, it just makes sense, right? Either an event occurs or it doesn't, right? So what do we do with how do we prove this one? Well, again, I will start, instead of just writing down the steps, I'll start with another visualization. And this one's even simpler because this now is just a Venn diagram for one set or one event. So here is my A. And so I'll shade what's inside of A. So these are all the elements in A. And then everything outside would be its complement. Right? So in fact, yeah, I can even label it. That's the complement there. And the key to this is noting that if I take the union of the set A with its complement, what do I get? Well, I get the entire sample space. I get the entire rectangle, right? Because either it's inside of A or not in A. So what we can say is, we can write, so since A union its complement is equal to the sample space, what if I took the probability of both sides? So then the probability of A union A complement will be the probability of S. Glance back at our list of axioms. And what did we say about the probability of the sample space, which is all the possible outcomes? That probability has to be 1, right? So that's where we use the axiom, right? The first axiom. And then because A and A complement are disjoint, they have no elements in common, I can write this as the sum of the probability of A and the probability of A complement, right? So let me just kind of annotate this. This fact is due to axiom 1. This fact over here is due to axiom 3. Now, to get the result that we want, simply isolate the probability of the complement. So subtract the probability of A from both sides, and that's our QED. So the probability of A complement is 1 minus the probability of A. All right? So we have two formulas now that we can use, and it's important to kind of put it in context. So let's just do a quick summary, kind of wrapping this up. Now in this particular video, I'm not going to do any examples. I wanted to present the results, give you the proof, and then the idea behind it, right? But let's just summarize what we have so far, and then going forward, we can utilize these results, right? So the general addition rule states this, right? So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. And this works for any two events. But a special case of this, and this special case is actually stated in it's what we used over here, axiom 3. But here's a special case. If A and B are disjoint or mutually exclusive, meaning they have no elements in common, like they don't overlap, right? Then what would happen is, since they have no elements in common, this probability here would be 0. So we end up with what the axiom states. So if we know that they're disjoint, this formula simplifies even more. So then the probability of A union B is equal to the probability of A plus the probability of B, right? But again, this is just a special case. And then the third result tells us how to find the probability of a complement. And it gives the relationship between the probability of a complement and the probability of the event, right? So definitely make a note of these. And then in subsequent videos, we will see how to actually utilize them. See you then.